September 7th, 1943. The Salerno beachhead, southern Italy. Oberingenieur Werner Schmidt's hands moved carefully over the captured American radio set, his fingers tracing the unfamiliar contours of what the intelligence brief had called an SCR-300. Around him, in the makeshift technical examination tent, 3 of Germany's finest radio engineers waited, barely containing their eagerness to dissect this piece of equipment that had fallen into Wehrmacht hands during the chaotic early hours of the Allied invasion. They had been told by Berlin that American portable communications were primitive, heavy, and unreliable. The Propaganda Ministerium's technical assessments had assured them that German engineering superiority extended to every aspect of military equipment. Yet something about the radio traffic intercepted during the landing had troubled the signals intelligence officers. American infantry units maintained constant, clear communication across distances that should have been impossible with backpack equipment. Their forward observers directed artillery fire with a precision that suggested radio systems far more sophisticated than propaganda had described. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The radio sat on the examination table, still attached to its frame and harness. It had been stripped from an American radio man killed in the fighting near Paestum. The operator's body had been removed, but his equipment remained intact, miraculously undamaged despite the violence that had taken his life. Schmidt carefully unbuckled the straps and lifted the main unit from its mounting. The weight surprised him. 35 pounds, perhaps slightly less. For a radio claiming 5-mile range, that was remarkably light. German portable transmitters of comparable capability weighed 50 pounds or more and required external battery packs that added another 20 pounds. He set the unit on the table and began his external examination. The case was heavy-gauge steel, painted olive drab, with rubber gaskets protecting every seam and connector. The construction quality was immediately apparent. This was not the crude field expedient he had expected. Every aspect of the design spoke to careful engineering and robust manufacturing. The top panel bore clear, simple markings in English: channel selector, volume control, push to talk, squelch. The controls were large, designed to be operated while wearing gloves. The layout was intuitive, requiring no technical knowledge to understand basic operation. Lieutenant Hans Krieger, a specialist in portable radio systems who had designed equipment for the Wehrmacht's mountain troops, leaned closer. "The waterproofing is exceptional. Look at these seals. This radio could be submerged and probably still function." Schmidt nodded. He had already noticed the attention to environmental protection. German portable radios required careful handling to prevent moisture damage. This American unit appeared designed to survive conditions that would destroy Wehrmacht equipment. He opened the battery compartment. 2 options were evident from the mounting brackets: a large battery case that attached to the bottom and a smaller internal battery space. The American engineers had provided flexibility: maximum range with the large battery, reduced weight with the small one. The operator could choose based on mission requirements. German portable radios offered no such options. You carried the specified battery or the radio did not function. The examination team began systematic testing. They connected the radio to a test battery, a 12-volt unit from a German signals truck. The power requirements were marked clearly on the unit. The radio drew approximately 2 amperes. Schmidt turned the power switch. A faint hum indicated the vacuum tubes warming up. Within seconds, the ready light illuminated. He rotated the channel selector. It moved smoothly through marked positions, each one precisely defined by a mechanical detent. The dial face showed 48 channels, numbered and spaced across the frequency range of 40 to 48 MHz. 48 channels. The number staggered him. German portable radios typically operated on a single frequency, perhaps 2 if equipped with alternative crystals. Changing frequencies required a trained technician and several minutes of adjustment. This American radio allowed an untrained operator to select any of 48 frequencies simply by rotating a knob. Krieger examined the channel selector mechanism more closely. It's all mechanical. No hand tuning, no technician adjustments. The operator simply selects a number, and the radio switches frequencies automatically. Everything retuned instantly. Schmidt removed the cover plates to examine the internal circuitry. What he discovered in the next 30 minutes would fundamentally alter his understanding of American manufacturing capability and the future direction of military communications. The radio was a masterpiece of miniaturization and integration. 18 vacuum tubes were mounted in precise sockets, each one accessible for replacement without special tools. The circuit board used printed wiring, a technique German engineers had considered but rejected as too difficult for field production. Every component was clearly marked with specifications and replacement codes. The transmitter section occupied the upper portion of the chassis. It was a frequency-modulated design, using a crystal-controlled oscillator, followed by multiple frequency multiplier stages. Schmidt had expected amplitude modulation, the standard for all German portable equipment. Frequency modulation was theoretically superior, providing static-free communication and resistance to interference, but it required significantly more complex circuits and precise frequency control. German engineers had concluded that FM was impractical for field equipment. The circuit complexity made it too expensive and too difficult to manufacture in quantity. Yet here was an FM transmitter, miniaturized into a backpack unit, mass-produced, and issued to common infantry soldiers. The receiver section revealed even greater sophistication. It was a double superheterodyne design with automatic frequency control circuits that locked onto signals and maintained tuning without operator adjustment. German portable receivers were simple regenerative designs, requiring constant manual tuning to compensate for battery voltage changes, temperature drift, and component aging. American receivers, it seemed, tuned themselves. Krieger focused on the frequency control system. This is impossible. Look at the crystal oscillator. It's temperature compensated. The frequency stability must be within a few parts per million across the entire operating temperature range. Schmidt examined the crystal unit. It was hermetically sealed in a metal holder, precision manufactured to tolerances that would require weeks of laboratory work in Germany. The crystal holder was marked with exact frequency specifications, 4.3 MHz. The transmitter and receiver both derived their frequencies from this single crystal through precise multiplication and mixing circuits. He carefully calculated the implications. To achieve 48 channels with crystal control, the Americans had developed frequency synthesis circuits of extraordinary sophistication. A single crystal generated a reference frequency. Electronic circuits multiplied and mixed this frequency to produce any of the 48 operating channels with precision that maintained frequency stability regardless of temperature, battery voltage, or component variations. German radio engineers had discussed similar systems in theoretical papers. No one had suggested they could be manufactured in portable equipment and mass-produced for field use. The modular construction became apparent as Schmidt continued his examination. Every major subsystem, transmitter, receiver, power supply, and frequency control, was a separate replaceable unit. An operator could remove a failed module and install a replacement in minutes without tools or technical knowledge. This approach required massive manufacturing capacity to produce spare modules, but it meant that American infantry maintained communications capability under conditions that would leave German forces radio silent for days while technicians performed field repairs. Most disturbing was the quality of individual components. Vacuum tubes were manufactured to tighter tolerances than German military specifications. Capacitors and resistors had stability ratings that German factories could not achieve in mass production. The entire radio was designed for assembly by semi-skilled workers, using simple procedures rather than requiring radio engineers with years of training. Lieutenant Krieger removed one of the vacuum tubes for closer examination. These tubes are commercial types, the same tubes used in American home radios. They've militarized civilian production rather than developing specialized military components. It's brilliant and terrifying at the same time. Schmidt understood immediately. German military tubes were custom designed for each application, requiring dedicated production lines and skilled technicians. American military tubes were civilized versions hardened for military service. Any factory producing home radios could shift to military production with minimal retooling. The manufacturing implications were staggering. The examination team spent the remainder of that day testing every function of the captured radio. They extended the antenna, a 10-foot collapsible whip that deployed in seconds. They connected the handset, noting its rugged construction and clear audio quality. They transmitted test signals and monitored the output on Wehrmacht, receiving equipment positioned at various distances. The SCR-300 performed exactly as American propaganda claimed. Clear, static-free voice communication out to 5 miles with the short antenna. Extended range to 8 miles or more with the long antenna and favorable terrain. The frequency modulation stripped away interference that made German amplitude modulation transmissions barely usable under combat conditions. The automatic frequency control meant that operators with minimal training could maintain perfect communications. No constant retuning. No frequency drift as batteries weakened or ambient temperature changed. Just reliable, clear communication whenever needed. By evening, Schmidt had drafted his initial report to Wehrmacht High Command. He chose his words carefully, knowing that his conclusions would contradict years of propaganda and intelligence assessments about American technical capabilities. The captured American SCR-300 represents a level of sophistication in portable military communications that Germany cannot match. The radio employs frequency modulation, crystal control, automatic frequency circuits, and modular construction that represent fundamental advantages impossible to overcome through superior tactics or operator skill. More critically, every aspect of the design reflects an industrial philosophy that Germany does not possess. This equipment is designed from the start for mass production by semi-skilled workers, operation by minimally trained soldiers, and maintenance through simple module replacement rather than technical repair. Schmidt estimated that Germany would need to build 15 specialized factories, train 30,000 additional workers, and invest resources equivalent to half the annual Luftwaffe electronics budget to produce comparable equipment. Even then, Germany lacked certain raw materials and manufacturing capabilities that American industry possessed. The conclusion was inescapable. American industrial capacity had made technological superiority militarily decisive. The frequency modulation, automatic circuits, and crystal control were not just technical features. They were evidence of an industrial philosophy and manufacturing capability that Germany could not match regardless of how many resources were devoted to the effort. The report reached Berlin on September 15, 1943. It was classified most secret and distributed to only a handful of senior officers in Wehrmacht High Command and the Reich Ministry of Armaments. The response was predictable. Silence. No new programs were authorized. No crash development efforts were initiated. The implications were too devastating to acknowledge publicly. But Technical Testing Station 12's work was only beginning. Over the following months, more American radio equipment fell into German hands. Each capture provided additional evidence of American technical and industrial superiority. An SCR-536 handheld radio, the famous handy-talkie, demonstrated miniaturization that German engineers had considered impossible. 5 vacuum tubes, complete transmitter and receiver, waterproof case, all in a package weighing 5 pounds. German portable radios of comparable function weighed 15 pounds and required external battery packs. The SCR-536 operated on a single crystal-controlled frequency between 3.5 and 6 MHz. It was simple, reliable, and producible in massive quantities. By war's end, over 130,000 units would be manufactured. More sophisticated equipment appeared as the Italian campaign progressed. An SCR-608 captured near Cassino in January 1944 revealed the full scope of American vehicular communications capability. This unit provided frequency-modulated voice and continuous wave communications across 80 separate channels spanning 27 to 39 MHz. The transmitter produced 25 watts of power. The receiver incorporated triple conversion superheterodyne circuits with crystal filter selectivity. Most significantly, the radio was designed for installation in tanks, where engine noise and electrical interference made amplitude modulation virtually unusable. Frequency modulation solved the problem completely. American tank crews maintained perfect communications, while German panzer commanders struggled with static-filled transmissions or resorted to hand signals. The technical intelligence reports flowing from Italy documented not just individual radio sets, but an entire communications philosophy. American forces maintained constant contact from squad level to theater command through multiple layers of radio networks. Squads had SCR-300 handy-talkies. Companies had SCR-300 backpack radios. Battalions had vehicle-mounted SCR-500 and 608 sets. Regiments had SCR-193 and 299 long-range equipment. Each level could communicate with the levels above and below, creating a web of connectivity that German forces could not match. More critically, all American radios used compatible frequency systems and interoperable equipment. A forward observer with an SCR-300 could contact an artillery battalion 20 kilometers away using an SCR-608 because both used frequency modulation on compatible frequencies with crystal-controlled stability. German forces operated multiple incompatible radio systems, each requiring different frequencies, different modulation types, and different operating procedures. By winter 1943, German signals intelligence had documented over 40 different American military radio types, from handheld transceivers to airborne command sets. Production estimates derived from captured serial numbers, and intelligence reports suggested that American factories were producing over 80,000 military radio sets monthly. German production, including all services and types, reached approximately 12,000 units monthly at peak capacity. The examination teams began analyzing captured American manufacturing documentation. Technical manuals, parts lists, and maintenance procedures revealed the infrastructure behind American equipment. Components were standardized across multiple radio types. Vacuum tubes used common base configurations. Crystals followed standard holder designs. Even hardware like screws, nuts, and bolts followed unified thread standards, allowing complete interchangeability. This standardization meant that American factories could shift production between different radio types without retooling. A plant producing SCR-508 transmitters could switch to SCR-608 units by changing only a few fixtures and component types. Parts from one radio type could often be salvaged to repair others. The entire system was designed for flexibility and scale. German manufacturing used custom components for each equipment type. The Tornfu B infantry radio shared almost no parts with the Fug 5 tank radio. Despite similar electrical functions, each type required dedicated production lines, unique test equipment, and specialized spare parts inventory. Changing production priorities required months of retooling and retraining. Oberingenieur Schmidt transferred to a larger technical intelligence facility in northern Italy by spring 1944. He spent increasing time analyzing American manufacturing methods rather than just equipment design. His reports to Berlin evolved from technical assessments of radio circuits to strategic warnings about industrial capacity. He documented the American electronics industry's explosive growth. Companies with names like Galvin Manufacturing, later called Motorola, had transformed from small radio manufacturers into massive military contractors. This company alone had received the contract to develop the SCR-300 in 1940. By 1943, they were producing thousands of units monthly. Western Electric, the manufacturing arm of the Bell telephone system, operated factories employing tens of thousands of workers, producing crystals, vacuum tubes, and complete radio sets. These companies had not existed as major military suppliers before 1941. The Americans had created an entire military electronics industry in less than 2 years by converting civilian factories, training new workers, and applying mass production techniques refined in automobile and consumer appliance manufacturing. The German radio industry, centered in Berlin, Munich, and Hamburg, remained organized as it had been in the 1920s. Small manufacturers produced specialized equipment using skilled craftsmen. Production quantities were measured in hundreds per month, not thousands per week. Quality was maintained through individual inspection and hand adjustment, not statistical process control and automated testing. Schmidt's December 1943 report to the Reich Ministry of Armaments was titled The American Radio Industry, an assessment of industrial capacity and strategic implications. It documented American electronics production in devastating detail. United States industry was producing annually what would take Germany 15 years to manufacture. The gap was not just technological, it was industrial, organizational, and philosophical. The report estimated that American factories could produce enough military radios to equip 1,000 divisions, though the Americans only fielded approximately 90 divisions. The surplus capacity meant that American forces had unlimited replacement equipment. Damaged radios were not repaired in the field. They were replaced. Outdated models were retired and sent to training units. Newer, better designs were continuously introduced, not as prototypes, but as mass-produced equipment distributed across entire theaters. German forces, meanwhile, carefully husbanded every radio. Field technicians performed repairs under combat conditions, cannibalizing parts from damaged sets to keep others operational. Replacement equipment arrived irregularly, if at all. Newer designs remained in limited production, because retooling would reduce output of existing models. The Wehrmacht operated radios designed in the early 1930s alongside newer equipment, creating maintenance nightmares and training difficulties. The crystal supply situation was particularly critical. By late 1943, German quartermasters estimated they needed 3 million precision crystals for existing radio equipment and planned upgrades. Domestic production capacity was approximately 150,000 crystals annually. Even if Germany devoted enormous resources to expanding crystal production, it would take over 15 years to produce 3 million units. The Americans, according to intelligence estimates, were producing over 20 million crystals annually. They had solved the quartz supply problem by finding deposits in Brazil, mining operations in Arkansas, and even synthetic crystal growing experiments. American crystals were not just abundant, they were superior in quality, achieving frequency stabilities that German laboratories could barely measure, let alone manufacture. The examination of captured American test equipment revealed another dimension of the industrial gap. American radio factories used automated test sets that measured frequency, power output, modulation quality, and sensitivity in seconds. These testers were themselves sophisticated electronic instruments produced in quantities that allowed every assembly line station to have dedicated test equipment. German factories used manual test procedures requiring skilled technicians in minutes per unit. One captured test set, a signal core frequency meter, became a prized possession of the technical testing facility. This single instrument, standard equipment in American factories, could measure radio frequencies with precision that required an entire German laboratory filled with separate oscillators, frequency standards, and measuring equipment. It had cost approximately $200 to manufacture. The equivalent German capability required equipment costing thousands of Reichsmarks and constant calibration by engineers. By early 1944, the message from technical intelligence was clear and terrifying. American communications superiority was absolute, irreversible, and growing. Every month, American factories produced more radios than Germany had in its entire military inventory. Every captured example showed incremental improvements, design refinements, and manufacturing sophistication that Germany could not match. The introduction of American radar systems in late 1943 drove home the message with even greater force. Radar was radio technology pushed to its ultimate extreme, using microwave frequencies, pulse techniques, and sophisticated signal processing. The Americans were mass-producing radar sets for ships, aircraft, and ground installations with the same industrial efficiency they applied to voice radios. A captured SCR-300 fire control radar examined in March 1944 demonstrated technical capabilities that German radar scientists had only theorized about. The set operated on the extremely high frequency of 3000 MHz, used a precision tracking mount with automatic following circuits, and achieved accuracy that allowed anti-aircraft guns to destroy enemy aircraft with devastating effectiveness. The SCR-300 weighed over 10,000 pounds and required a dedicated vehicle for transport, yet American factories were producing them by the hundreds. German radar development had focused on systems operating below 1,000 MHz because German industry could not manufacture the specialized vacuum tubes needed for higher frequencies. The magnetron tubes used in American microwave radar required precision machining, exotic materials, and manufacturing techniques that Germany did not possess. Even when German scientists designed microwave radar systems on paper, they could not be built because the components simply did not exist in German industry. The systematic examination of captured American equipment continued through 1944 as Allied forces advanced up the Italian peninsula and prepared for the invasion of France. Each new example added to the mountain of evidence documenting American technical superiority. Improved radios appeared regularly. The SCR-609, introduced in mid-1944, provided frequency modulation aircraft communication with hundreds of crystal control channels and near-instantaneous frequency switching. Most significantly, American equipment reliability improved continuously. Early production SCR-300 radios had occasional problems with moisture ingress and battery contacts. Captured examples from late 1944 showed redesigned cases, improved seals, and modified circuits that eliminated these issues. The Americans were not just building equipment, they were continuously improving it based on field experience and incorporating lessons learned into ongoing production. German equipment, in contrast, often degraded in quality as the war progressed. Material shortages forced substitution of inferior components. Skilled workers were drafted into combat units, replaced by less experienced personnel. Quality control suffered as factories focused on quantity over reliability. Radios that should have lasted for years began failing after months of service. By the time of the Normandy invasion in June 1944, German technical intelligence had documented the complete picture of American communications superiority. Allied forces landing in France carried more radios than the entire German army possessed. Every Allied company had radio contact with battalion headquarters. Every Allied battalion could reach division command. Artillery forward observers directed fire from dozens of kilometers away with perfect accuracy because their radios never lost contact. German commanders attempting to coordinate defences found their communications breaking down under Allied jamming, artillery fire, and the simple chaos of battle. Radios that worked perfectly on test ranges failed in combat. Crystal oscillators drifted off frequency in the Norman summer heat, making contact between units impossible. Battery-powered sets ran down quickly because replacement batteries were unavailable. The communications network that German doctrine assumed would exist simply ceased to function under combat stress. The technical reports flowing back to Berlin became increasingly desperate in tone. Oberingenieur Schmidt, now attached to Wehrmacht operations staff, wrote in August 1944 that Germany had already lost the electronic war. American jamming equipment, direction-finding systems, and signal intelligence capabilities allowed the Allies to locate and target any German radio transmission within minutes. German codes were broken, frequencies were monitored, and movements were tracked through radio traffic analysis. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The final collapse came in late 1944 and early 1945, as Germany's industrial base disintegrated under Allied bombing. Factories producing radio equipment were priority targets. Telefunken's Berlin facilities were destroyed in November 1944. Lorenz's production plants in Stuttgart were bombed repeatedly. The crystal production facility in the Sudetenland fell to Soviet forces in January 1945. By March 1945, German radio production had essentially ceased. Existing equipment continued to function, maintained by increasingly desperate field technicians who cannibalized parts from damaged sets and improvised repairs with whatever materials they could find. Replacement radios simply did not exist. When a headquarters radio failed, commanders lost contact with their units. When tank radios broke down, armored formations became isolated groups of vehicles unable to coordinate action. The Americans, meanwhile, continued improving their equipment even as victory approached. New radios introduced in early 1945 offered enhanced range, additional channels, and improved reliability. Production continued at full capacity, not because more radios were needed, but because the industrial machine could not easily be stopped. By May 1945, American depots were filled with excess radio equipment that would never be used in combat. The end came on May 8, 1945. Germany surrendered unconditionally to Allied forces. Among the items catalogued by occupation, authorities were the technical intelligence reports from Salerno, Sicily, and throughout Italy. These documents, classified most secret by German authorities and hidden in salt mines and underground archives, provided Allied investigators with a unique perspective on their own equipment. American technical teams, searching through German facilities in the summer of 1945, were surprised to discover how thoroughly the Germans had examined captured American radios. The reports were accurate, detailed, and professionally done. They correctly identified American technical advantages and honestly assessed German inability to match American capabilities. One report, written by Oberingenieur Werner Schmidt in April 1945, as Soviet forces closed on Berlin, served as his final testament to the technical war. He wrote that Germany's defeat was inevitable from the moment German engineers opened the first captured American radio in Salerno. The frequency modulation, automatic circuits, and modular design revealed an industrial philosophy that Germany could never match. The Americans had industrialized warfare itself, applying mass production techniques to every aspect of military equipment. Schmidt concluded that future wars would be won not by the side with better soldiers or superior tactics, but by the side with greater industrial capacity to produce high-technology equipment in overwhelming quantities. Germany had excellent soldiers, competent generals, and adequate tactics. What Germany lacked was an industrial base capable of matching American production. This lack was most clearly visible in something as simple as a radio crystal, ground to precision tolerances by teenage girls, in factories that produced millions of units annually, while German laboratories struggled to make thousands. The post-war fate of the German engineers who examined captured American equipment reflected the realities of the New World Order. Werner Schmidt was recruited by American authorities in 1946 and spent 2 years documenting German radio technology for United States intelligence. He later worked as a consultant to American electronics companies, helping them understand and improve upon German innovations worth salvaging. Many of his colleagues followed similar paths. The brain drain from Germany to America, formalized in Operation Paperclip and similar programs, transferred thousands of German scientists and engineers to the United States. They brought knowledge of German technology, but more importantly, they learned American industrial methods, mass production techniques, and the organizational philosophy that had made American victory inevitable. In 1952, Schmidt published a technical paper in the Institute of Radio Engineers Proceedings titled Comparative Analysis of German and American Military Radio Design Philosophy, 1939 to 1945. The paper, based on his wartime experience examining captured American equipment, documented in academic language what he had reported to Wehrmacht High Command nearly a decade earlier. American radio design, he wrote, prioritized ease of manufacture, simplicity of operation, and reliability under all conditions over technical sophistication or component efficiency. German design sought technical excellence, theoretical perfection, and component economy, assuming that skilled operators would compensate for equipment limitations. One philosophy scaled to millions of units and global deployment, the other did not. The paper became required reading in engineering schools and military technical services. It influenced a generation of American engineers who designed equipment for the Cold War, the space race, and the computer revolution. The lessons learned from German engineers examining American equipment shaped American technological dominance for decades. By the 1980s, many surviving German engineers who had worked in technical intelligence during World War II gathered for reunions and historical conferences. They shared memories, compared notes, and reflected on their experiences. Werner Schmidt, then in his 70s, gave presentations on his work examining captured American radios in Salerno and throughout Italy. At a conference in Munich in 1986, he displayed photographs of the first SCR-300 his team had examined in September 1943. The images showed young German engineers leaning over the opened radio case, measuring circuits, documenting components, and struggling to understand what they were seeing. Schmidt told his audience that the moment they removed the cover and saw the Kara, crystal-controlled frequency synthesis system with automatic tuning circuits installed in a standard infantry backpack radio, he knew Germany had already lost the war. The frequency modulation transceiver, a sophisticated device requiring 18 vacuum tubes, precision crystals, and automatic control circuits, represented the intersection of physics, engineering, and industrial organization. It was not a complex device in principle. Any competent laboratory could build one. But to produce 50,000 units to standard quality, with perfect interchangeability at a cost low enough for issue to infantry companies, required an industrial infrastructure that Germany simply did not possess. That infrastructure, created in America between 1941 and 1945, did not dissolve when the war ended. It expanded and evolved, producing transistors, integrated circuits, microprocessors, and eventually the computers and communication systems that define the modern world. The same companies that had mass-produced radio crystals for SCR-300 backpack radios later produced semiconductors for space missions, microchips for personal computers, and the components that enabled global telecommunications. The lessons learned from German engineers examining American equipment in Italy became part of the foundation of modern technology. Design for manufacture, standardize components, train operators simply, build testing into the process, scale production to meet demand. These principles, visible in every aspect of American radio equipment in World War II, became the standard methodology for all high-technology industries. In 1995, on the 50th anniversary of the war's end, the Smithsonian Institution opened an exhibit titled Communications and Victory, The Radio War, 1939 to 1945. Among the displays was an SCR-300 backpack radio, serial number matching a unit examined by German engineers in Italy in 1944. The radio had been recovered from German archives and returned to the United States as part of a cultural exchange program. Beside the radio, the exhibit displayed excerpts from German technical intelligence reports, translated into English, documenting the examination process and findings. Visitors could read Schmidt's observations about crystal quality, circuit design, and manufacturing sophistication. They could see photographs of German engineers measuring components, testing circuits, and recording data. The exhibit made clear that German technical experts recognized American superiority, reported it accurately to their superiors, and understood its implications. The exhibit also displayed German radio equipment for comparison. A torn Fu B infantry radio sat beside the American SCR-300, allowing direct visual comparison. The German radio was larger, heavier, more complex to operate, and less capable in every measurable way. It represented excellent engineering constrained by limited industrial capacity. The American radio represented adequate engineering, multiplied by unlimited industrial resources. The curator's notes explained that the exhibit was not about praising American technology or denigrating German equipment. Both sides had competent engineers who designed effective equipment within their constraints. The difference was not intelligence, training, or theoretical knowledge. The difference was industrial philosophy and manufacturing capacity. Americans built systems that worked reliably when operated by minimally trained users. Germans built systems that worked brilliantly when operated by highly trained experts. One approach scaled to global war. The other did not. The final display in the exhibit was a small glass case containing a single frequency crystal recovered from an SCR-300 examined in Italy. The crystal, no larger than a postage stamp, was precisely cut quartz in a hermetically sealed metal holder. The label explained that this crystal, one of several used in the frequency control system of a standard American infantry radio, represented approximately 30 hours of German skilled labor to duplicate. The Americans had produced over 50 million such crystals during the war, an output that would have required every German radio technician to work for 400 years. The exhibit attracted over 200,000 visitors during its year-long run. Many were veterans who had operated the radio equipment displayed. Some were engineers interested in technology history. A few were historians studying the industrial aspects of warfare, all left with a deeper understanding of how industrial capacity determines military outcomes. Werner Schmidt died in 1997 at age 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine noted his contributions to radio technology, his work in technical intelligence during World War II, and his post-war career helping American companies understand German innovations. The obituary also mentioned his lifelong insistence that Germany's defeat was determined not on battlefields but in factories, not by soldiers but by production workers, not through tactical failures but through industrial limitations. His papers, donated to the Deutsches Museum in Munich, included over 1,500 pages of technical reports, circuit diagrams, component specifications, and strategic assessments, written between 1943 and 1945. These documents provided historians with detailed insight into how German technical experts viewed American equipment and what they reported to Wehrmacht High Command. Perhaps the most poignant document in the collection was a personal letter Schmidt wrote to his wife in April 1945 as Berlin fell to Soviet forces. He had sent his family to relatives in Bavaria months earlier and remained in Berlin, performing final technical assessments until ordered to evacuate. In the letter, he wrote that he was about to destroy all classified documents and equipment to prevent capture. He reflected on the 2 years spent examining American equipment, from the first SCR-300 in Salerno to the latest radar sets captured in the Ardennes. Every example, he wrote, confirmed the same conclusion. America possessed not just better equipment, but a fundamentally different approach to warfare. They had industrialized everything from radio crystals to entire armies, applying the same mass production philosophy that built automobiles and refrigerators. Germany, Schmidt wrote, had tried to fight an industrial war with craftsman methods. It was not that German technology was inferior. In many areas, German theoretical knowledge exceeded American. But theory does not win wars. Production capacity wins wars. The side that can build more tanks, more aircraft, more radios, and more everything will eventually overwhelm any opponent, no matter how skilled or brave. He concluded the letter with a prediction. The next war, if it came, would be even more industrial than the last. Victory would go to the nation with the greatest manufacturing capacity, the most advanced technology, and the ability to produce precision components in unlimited quantities. America had demonstrated these capabilities between 1941 and 1945. Any future opponent would need to match or exceed American industrial power, something Schmidt believed was impossible for any single nation. History proved him correct. The Cold War that followed World War II became a competition of industrial capacity, technological innovation, and manufacturing capability. The Soviet Union, despite continental resources and massive population, could not match American electronics production, computer technology, or industrial automation. The gap that Schmidt identified in radio crystals in 1943 expanded to encompass semiconductors, microprocessors, and integrated circuits. The story of German technicians examining captured American radio equipment is ultimately a story about industrial warfare and the revolution in manufacturing that occurred in America during World War II. It is about the transformation of warfare from an activity primarily determined by tactics, training, and courage to one determined by industrial capacity, technological sophistication, and manufacturing efficiency. The frequency modulation transceivers that so impressed Schmidt and his colleagues were not magic. They were precision engineering, yes, but more importantly, they were precision engineering scaled to mass production. American industry had learned to produce tens of thousands of units to identical specifications, something that had never been done before at that scale with such sophisticated equipment. This capability, developed for portable radios, extended to every aspect of placed military equipment and eventually to every consumer product America manufactured. The lessons learned by German engineers examining American equipment in Salerno, Sicily, and throughout Italy were harsh but clear. Superior individual equipment means nothing if it cannot be produced in quantity. Sophisticated technology is useless if operators cannot reliably use it. Theoretical excellence is worthless if manufacturing cannot achieve it consistently. Industrial capacity, properly organized and directed, defeats everything else. These lessons, purchased at the cost of Germany's defeat, became the foundation of modern manufacturing philosophy. Design for production, build in quality, train users effectively, support equipment properly, scale to demand. The principles visible in American radio equipment in World War II now govern global manufacturing in every industry. In the end, the story that began with Oberingenieur Werner Schmidt opening a captured radio case in Salerno in September 1943 concluded with the complete transformation of how nations prepare for and conduct warfare. The backpack radio transceiver, that 35-pound piece of precision-engineered electronics, became a symbol of the industrial revolution in military affairs. It represented the moment when victory stopped being determined primarily by battlefield prowess and started being determined by factory output. The German engineers who examined American equipment understood this transformation as it happened. Their reports documented not just technical specifications but the end of one kind of warfare and the beginning of another. They witnessed, analyzed, and reported the future of conflict. That their warnings went unheeded in Berlin did not diminish the accuracy of their assessments. Today, the principles they identified, mass production of precision components, industrial automation, standardization for interchangeability, and design for manufacturability, are fundamental to every high-technology industry. The direct line runs from frequency crystals ground in American factories in 1943 to microprocessors produced in Asian foundries in the 21st century. The industrial philosophy remains the same, only the scale has changed. The German technicians who tested captured American radio equipment in 1943 were not just examining communications devices. They were witnessing the future of warfare, technology, and industrial organization. Their detailed reports, classified and filed away during the war, eventually became historical documents that explained not just why Germany lost, but how industrial capacity determines the outcome of modern conflicts. Their conclusion, written in technical language but unmistakable in meaning, was that Germany had challenged the world's greatest industrial power with inadequate manufacturing capacity. The radio transceiver, with its crystal-controlled frequency modulation and automatic circuits produced by American workers in quantities Germany could never match, told the entire story. Industrial warfare demands industrial capacity. Without it, no amount of tactical skill, technological innovation, or individual courage can achieve victory. That lesson, learned by German engineers examining American radio equipment in underground laboratories across occupied Europe, remains relevant today. In an age of microelectronics, satellite communications, and computer-controlled warfare, the fundamental truth remains unchanged. The side with greater industrial capacity to produce high-technology equipment in overwhelming quantities will ultimately prevail. The Americans proved that principle between 1941 and 1945. The world has been adapting to its implications ever since. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.